In this video, we're going to talk about model tuning, interpretation, and deployment. But first, let's remember about a few concepts. In this first module, we talk about parameters and hyperparameters. As a refresher, hyperparameters are parameters whose value control the learning process and determine the values of model parameters that a learning algorithm ends up learning. In this slide, hyperparameters are said to be external to the model because the model cannot change its value during learning or training. And this is what is depicted here. During model training, we get the best model parameters, but the hyperparameters are set before that. Here is a list of examples of hyperparameters that are applied to the different machine learning algorithms and that you may encounter during the tutorials or exercises. We're not going to go over this, it's just to give you a reference in case you need to identify one for your purpose. Another concept we should review, remember, is bias and variance. Bias is the error that arises due to the model making wrong assumptions on the parameters in the underlying data. It occurs when a model predictions consistently deviate in a particular direction, reflecting a systematic error. The bias error is the difference between the expected or predicted value of the model estimator and the true or actual value which we are trying to predict. As an example, a linear model, which assumes linearity between the dependent and independent variable, has high bias compared with a decision tree model, which has no assumption on the structure of data. In the case of variance, this error arises due to model sensitivity to fluctuation in dataset, such as new data points, randomness, and noise, making the model too sensitive to outliers and random noise and leading to bad generalization. Let's review again this graph where we have bias versus variance, and we want to focus on the four extremes, four quadrants of this graph. Remember that each dot in this image represents one instance of training, hence one trained model. What changes from dot to dot is that is another training data. It's the use of a different training data. So if the trained model's error on the test data is low, its dots should land inside the red circle. When the dots cluster together, it means the underlying trained models are consistent. And when they are spread, they mean that they have high variance. So here we see the four extremes, and the models on the bottom left with low bias and low variance is what we are trying to achieve. Those have good general structure of data and data patterns and relationships. Those with high bias and low variance, which are on the top left, make consistent predictions irrespective of datasets, tend to have consistency, but they might be off of the desired prediction. The ones on the bottom right are those with very low bias but high variance, and these are spread and they can generalize to some extent and perform well on average but are sensitive to the data. And those with high variance and high bias do not learn necessary relationships and are sensitive to data outliers and noise. So they don't have consistency and they are spread out. So within these cases, we have the really extremes, cases of bias and variance, where cases of, we saw before, for very high bias and low variance is called underfitting, and cases with very high variance and low bias is called overfitting. So underfitting considers that the model will have extreme low variance and high bias, as we just indicated. The model will fail to learn anything about the data, underlying patterns and relationships. The case of overfitting, the model will have very low bias, no assumption of the data structure, but very high variance, focusing too much on the training data. The model is so specific to the training data that fails to do any generalization over new data. Obviously, there's a balance that we want to achieve, and it can be shown in this graph. We want to get models that compromise both bias and variance. And we can calculate this generalization error, which includes the bias error and variance errors that we can, in a way, manipulate, whereas the irreducible error are those errors that get introduced due to the noise in the training data itself and not much that we can do. Now let's move to tuning the model. One way of doing that is through cross-validation. It's the most prevalent practice for tuning the machine learning models. It uses the same data to build different models and also tune their hyperparameters using a simple data partitioning strategy. These are useful when we have less data observations and cannot segregate specific partitions of a data as validation set. So I'm going to explain in a moment. So there are at least two strategies for cross-validation. There are different strategies for cross-validation. One is called live-on-out cross-validation, or LOLOCV, and it is a special case of k-fold cross-validation, where k is the number of data points in our dataset. That is, we leave out one observation as the test set and then train the model on all other points. After we do that, we aggregate the performance across all the iterations. In the k-fold cross-validation, we split the training dataset into k equal subsets. And out of these k subsets, we train the model on the k-1 and keep one subset as a validation set. This process is repeated k times over the error, and the error is averaged across all these models. For each iteration, the model is trained on a different subset. For tuning hyperparameters, there are different strategies. One is called grid search and the other one randomized search. In the case of grid search, we specify a grid of value of hyperparameters we want to try out and optimize to get the best parameter combinations. Then we build the models on each of those values using cross-validation and report the best parameters combination in the whole grid. So the output will be the model using the best combination. The problem with this is that we need to manually provide the actual parameters that may not be the most optimal ones. The randomized search is a modification of this grid search, as it takes the input for grid elements as in normal grid search, but in this case it can also take distributions and input. We get the parameter values from certain distribution and control the number of iterations. In this way, we can identify the final set of hyperparameters that we will use for training our model. Let's talk about model interpretation now. Some of the machine learning models use interpretable algorithms. For example, a decision tree will give you importance of all the variables as an output. Some other models are interpretable by nature, and many models in machine learning are black box and hard to interpret. So model interpretation can help data scientists understand the interaction among the different features that can lead to better feature engineering and enhance performance. It can also help to compare models and explain the results better to the stakeholders. Skater is an open-source Python framework to provide model-agnostic interpretation of predictive models. The philosophy of Skater is that all the models should be evaluated as black boxes, and decision criteria of the models are inferred and interpreted based on input perturbations and observing the corresponding output predictions. And Skater enabled us to do both global and local interpretations. Now let's move to the final piece of our talk, which is about deployment. The simplest way to deploy a model is to persist the final model on permanent media like hard drive and then use it for making predictions in the future. This deployment scheme performs the necessary data transformation on the raw data and then reads the model from the permanent data store. Once we have the data and the model, we can make the prediction. It follows FAIR data practices. Another one is custom development, and this is another option for deployment where you develop the implementation of a model prediction method separately. The output of a machine learning model is the values of parameters that were learned. So we can extract these parameter values and use them for prediction by doing mathematical operations on new data using structured parameters. Here are the references. Thank you.